All right, let's talk about what we are doing today on your asynchronous Wednesday day of learning. Basically, we are going to introduce some new content that if you've already done your Edmentum will not be new. You've already seen this, but we're just going to dive a little bit more in depth into the ideas of atomic mass, isotopes, and ions. So the way I'm going to do this, I'm actually just going to share my screen for my whiteboard like I normally would in class. So you guys should be seeing the screen here. I'm going to also turn off my video. So all that you see here is the screen. I'm going to be walking through and working through this with you today. I'm going to be writing some things down. Feel free to be taking your own notes with you. That would be very, very wise to do. I will also be putting for tomorrow, you will be getting a review, and that review will have practice problems similar to the ones that we do like this today. So if you're looking for more problems and how to prepare for that quiz, please check tomorrow for your review. Anyway, let's recap what we know about atomic number. We know a lot about atomic number. Atomic number is pretty straightforward, right? We find it in the top corner of our element, and it tells us the number of protons or number of P+. I'm actually going to make my pen smaller. That's just too much. It tells us the number of protons, and coincidentally would also tell us what? It would also actually tell us the number of electrons for what? For a neutral atom. Okay, so important caveat there. It'll tell us the number of protons always and number of electrons for a neutral atom. Now, let's talk mass number. Okay, what do we remember about mass number? Mass number is equal to that number of protons plus your number of neutrons. So if you're given mass number, you can find number of neutrons. How would you do that? You'd use this formula right here. Mass number minus that number of protons equals how many neutrons you're dealing with. Okay, make sure you write these things down. You're following along. This makes sense. Reach out if it doesn't. Okay, that should all be reviewed. Now let's talk into things that aren't necessarily going to be reviewed. We introduced atomic mass on Monday and Tuesday for those of you who had different days. And what we talked about was atomic mass was that weighted average mass of the isotopes of that element, right? It is the, I'll write it real small right here. It is the weighted average mass of all the isotopes for an element. I wrote that really small. That's okay. That's just so that you guys have that there. The weighted average mass for all the isotopes of an element. We talked about how isotopes of an element are basically when you have a different number of neutrons for the same atom of an element. So we'll talk about more of that later. But I want to introduce this thing called the atomic mass unit. Because whenever you look at a periodic table, and I can't believe I didn't pull up a periodic table, so as I'm talking, I'm going to be pulling one of those up. But basically, whenever you look at a periodic table, what you should be seeing, right? And here is my periodic table for you. Okay. Whenever you see a periodic table, you should be seeing this value down here at the bottom, that 1.0079. We know very clearly that is our atomic mass, but what's the unit? We always need units. We always have units associated, and there's not one written on the periodic table. Basically, atomic mass has its own unit, and I'm going to come back to the whiteboard here. But atomic mass has its own unit called the AMU, or atomic mass unit. And how we found that AMU, I'm not going to ask you how we found this, so don't worry about writing this down. But how we found that AMU is it's 1/12 of the mass of a standard carbon atom, or it's 1/12 of the mass of a carbon-12 atom, isotope number 12. And so scientists defined that, and it was actually very, very nearly equal the mass of a proton or the mass of a neutron, right? But what having a standardized AMU allows us to do is that it allows us to give mass to these subatomic particles, which in reality are too small for any existing mass unless we go far beyond what we know with prefixes. So we kind of created that own atomic mass unit. And we're going to talk more about how we can not translate, but how we can use atomic mass units in grams interchangeably later. But I just want to introduce what that is, right? It was derived from 1/4, or I'm sorry, not 1/4, 1/12 of the mass, right, of a carbon-12 atom. But yeah, going back to atomic mass, we find that by taking that weighted average of all those isotopes. That's what we find on the periodic table, but you haven't really talked about what an isotope is. So I'm here to do that with you now. And what we know about an isotope is that it is, let's get this definition up for you. So an isotope, let's go, are atoms with the same number of protons, but a different number of neutrons. Isotopes are defined as atoms with the same number of protons, but with a different number of neutrons. So that's where you can have stuff like carbon-12, or you can have things like carbon-13. What you're saying here is that carbon-12 has 6 protons, 6 neutrons, right? 6 protons, 6 neutrons. And what you're saying here is that carbon-13 will still have 6 protons, right? Because that never changes. But how many neutrons? It would have 7 neutrons, okay? So we have 2 main ways of writing these isotopes. There's this full formation, or this long form, that you would just say, write out the full name of that element, like carbon-12. That would be that long form way of writing an isotope. But another way that we have is what's called isotope notation. Okay, so I love using isotope notation, and what that looks like is this. You'd simply take the symbol of the element you have in question. So we're dealing with carbon. On the top, you write its mass number, and on the bottom, its atomic number. So let me put that right here. This is mass number on top and atomic number on bottom. Okay, that's known as isotope notation. So what I can do is technically look at this isotope notation and know 3 things about it. I know that it has a mass number of 12, which means it has 6 protons and now 6 neutrons. And then a neutral atom would have 6 electrons as well. Okay, so we could write it like that, or if you come over here, the isotope notation for carbon-13 would be basically the same. But it would just have a different mass number up there on top. There are going to be isotope notation practice problems for you to do on that quiz review. That is Thursday and Friday's assignment. So please make sure you go look at that quiz review and you practice isotope notation. But I just wanted to very quickly go over isotopes and talk about what are they. They are just atoms with a different number of neutrons. And we know that atoms with neutrons and protons, right, those numbers added together give us our what? They give us our mass number. Okay, so now let's move on to this thing called relative abundance. A couple of you guys were in classes where I talked about this, but relative abundance is really where we tie in atomic mass and isotopes by talking about relative abundance. So let's use a really common example in chemistry. Let's use potassium, right? Element K, potassium. So we know that potassium has 3 major isotopes, right? Those 3 major isotopes are potassium-39, they are potassium-40, and potassium-41, right? So we know that there are 3 major isotopes that potassium exists in nature. Now, what we also know about this, right? What we also know about potassium, I'm trying to pull up its relative abundances. I'm trying to find them. And great. So what we also know about this potassium is that, wow, hold on. I'm having trouble finding this. 20, okay, there it is. What we know about this potassium is that the relative abundance here of potassium-39 is 93 Okay, and the relative abundance of potassium 40, right? We know that to be 0.01%, pretty small. And what we also know, the relative abundance of potassium 41 is found to be 6.73%. If you add all those percentages up, they should add up to 100. But this tells us just the percentage in nature that we find each of these isotopes. So 93% of the time, if we're dealing with potassium in our Earth, it is going to be potassium 39, meaning it has 19 protons and 20 electrons, because potassium is element 19. So those three, and I'll just draw them over here. Oop, I'm going to redo that. Those three isotopes written in isotope notation. I'll write them over here just so that you can see. But those three isotopes would look like this. Of course, they'd all start with K. In the top left, what goes here? It is the mass number. And you may be thinking, Mr. Lee, that's where we find atomic number. Not an isotope notation. We will see mass number followed by atomic number. And I'm going to draw a little bit of division so that you can see, or here, even better, I'll separate these a little bit so that you can see these a little bit more isolated and they don't get all jumbled up. But those are your three ways of representing potassium in isotope notation. Mass number on top, atomic number on bottom. So continuing on, we don't have a crazy amount of time. And so I want to make sure that we hit relative abundance a little bit further. What we know is relative abundance and mass number, or atomic mass, and isotopes all blend in. How do we know that? Is because atomic mass, right? Atomic mass is whenever we take the weighted average using these relative abundances. So I'm going to show you how to calculate atomic mass of potassium using these relative abundances, okay? Very simply, how we're going to do this, and this should actually go down here in relative abundance practice, but we'll just have more time. But how we're going to do this is we're going to take this potassium 39. Normally you're given an actual atomic mass, but we're just going to take the mass number. We're going to take potassium 39 and we're going to multiply it by this 93.26 as a percent. And we know about percents is that you must move the decimal over 2 places or divide by 100 when dealing with a percent. So you're going to add that to your mass number of your next. Ooh, wow, this one's even more zeros, right? Because we moved this 2 spaces over by dividing by 100. That's how you transform percents into decimals. And then you also have this one right here, 6.73. Oop, can't write it like that. What do I have to write it as? 0.0673. If you're confused on that step, all that I did was I took these values, these percentages, and divided them by 10 to actually reflect how we calculate the atomic mass here. Basically, we would then multiply these values together, right? 39 times 0.9326. Let me do that here. You should have your scientific calculator with you. But we do 39 times 0.9326, and we get 36.3714, right? And then you do the same over here. 40 times 0.0001. Wow, okay? And we go 0.004. And then finally, we go 41 times, ooh, wait, we've already written that up there. I put that in my calculator. 41 times 0.067, and I get 2.747. So now I add those values up together, 2.747 together plus 0.004 plus, hold on, I didn't type that in right. Let's try this again. 2.747 plus 0.004 plus 36.3713. No, I'm not showing my screen at this point. You're not missing anything, so fear not. And basically, whenever I add those three together, I get this value, 39.1223, okay, AMUs. If you compare that to a theoretical periodic table, if you compare that to the mass of potassium on the periodic table, the one I showed you earlier has it at 39.098. So you may say, Mr. Lee, why is there a discrepancy there? Well, it's because I used mass numbers instead of atomic masses. We'll talk about that more later, because what I mean by that is this value 39, once you actually apply the mass of the protons and neutrons, it'll give it some decimals. But for what I'm giving you, this is perfect. So you have found the atomic mass of potassium, right? Atomic mass equals that. Let's do another practice problem because these are really important to go over, okay? This practice problem, ooh, wow. I'm gonna move that like that. That should have been locked in. Anyway, so let's do this practice problem. Calculate the elemental atomic mass of magnesium if the naturally occurring isotopes are magnesium 24, 25, and 26. So here they've given us those three, magnesium 24, 25, and 26. We have the relative atomic masses. And again, you're like, Mr. Lee, I thought atomic mass was the averages. In this case, we're talking about they've actually found the weight of each proton and the weight of each neutron, and they've found the mass of it, which if you notice, they're really close to these whole numbers. So it's like we're dealing with 24, 25, 26, etc. So that's what that means. So don't get confused by that. We're going to find the elemental atomic mass using this table of information we're given. So first things first, we want to take this atomic mass and we want to simply multiply it by what? That isotopic abundance, or 0.7870, right? All I did was I moved that decimal over 2 places. Let's do it again here because we're going to add these together. We're going to go with this value and multiply it by 0.1013. Again, where did I get that? 1, 2. Great. And then finally, let's do the same with this right here. We're going to take 0.1117. We're going to multiply these 3 values together. I'm going to do so now. Okay. I'm going to save you guys some time and just talk over the mic while we get this figured out. Bada bing, bada boom. Okay. Plugged it into my calculator, and the value that I get, I totally didn't just look over my shoulder and look at the periodic table and not calculate these on my own. But the value that I get is 24.3 atomic mass units. So that's what we have found to be the elemental atomic mass of magnesium. Okay. So when you're given isotopes, you multiply their abundances as decimals by the mass number or relative atomic mass that we're looking at for that isotope. Okay. Cool. Awesome. Last bit of information. We already introed what an ion was, and I want to go over what an ion is again with you. Okay? We didn't give this a formal name, but basically ions are atoms of the same elements with uneven number, let's put an "and" in there, with an uneven number of protons and, not neutrons, electrons. Ions are atoms of the same element with an uneven number of protons and electrons, ultimately giving us a charge. So for example, if I had, and I'll give myself some more space over here. If I had, let's do oxygen, right? So if I had oxygen, we would naturally know by looking at the periodic table how many protons oxygen has. Well, once we have studied up enough, we would get to know that oxygen has 8 protons. Let's say we have oxygen with its mass of 16. We'll deal with that isotope. From this information, we'd know we have 8 protons, 8 neutrons, and 8 electrons. Now, ions are whenever that's not the case. Say we're dealing with oxygen 2 negative. Okay, we now have an ion because we have a charge. If you see a charge, you're dealing with an ion, right? And so you have an uneven number of both of these values. And so both of these values being protons and electrons, we still know we have 8 protons because that's never going to change. And how many electrons would we have? Well, remember, right? If we have a 2 negative charge, that means we have 2 more negatives than we do positives. So that means if we have 8 protons, we have an 8 positive charge there. And if we overall have a 2 negative, all we're setting up is this 8 plus question mark, or x, equals -2. What's going to give us -2 there? Oh, wow. I shouldn't have done that example. Please disregard everything I did because you would have said -10, and it's not -10. It is 10 multiplied by each negative. So if that confused you, please just skip over that part. But basically, since we have 2 extra negatives, we know that we need to have 2 electrons here. So that would be an ion of oxygen. Let me do one more example over here with you to clear up for the confusion I just did. If you saw something like this, 37, 17 Cl negative. This is a blend of ions in an isotopic notation. So what we could do here is interpret from this information three things. So we're going to interpret proton number, neutron number, and electron number. Stop right now. I want you to try this on your own, right? I want you to pause the video, try to calculate this on your own, and then come back and see if you did it correctly. Okay, great. If you're back, that means you've hopefully done this on your own, and you're going to see if you got it correct. Well, first of all, protons, that's the easiest part. Atomic number right there. Chlorine, it has an atomic number of 17, therefore it has 17 protons. Okay, next bit, mass number equals what? It equals protons plus neutrons. So if we do 37 equals 17 plus some number of neutrons, we know that we have 20 neutrons. So we have 17 protons, we have 20 neutrons. Let's try that again. That looks a little bit better. 20 neutrons. I'm just now realizing my N's look like U's. 20 neutrons. And then finally, how many electrons would we have? Naturally, we would think 17, right? Because electrons is normally equal to our number of protons. However, now we don't have 17. Why? Because we're dealing with an ion, right? So when we're dealing with an ion, what do we have to do? We have to account for this uneven amount. We have extra negatives here, so we must have 18 electrons because 18 cancels out 17 and leaves over an extra negative. Okay, that's ions. We just did our ion practice over there. You're going to have a quiz review that it should be posted by Wednesday early morning with a whole bunch of practice problems and a whole bunch of things to make sure you go over. Hopefully this was informative. Hopefully this helped. Reach out to me. I have no live classes and I'd love to hop on a Zoom. If you're confused, have an awesome day and peace.